Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be covering topics for your Math 200 class for Chapter 9, which is all about estimating the value of a parameter. So we're going to start with, it looks like my screen is a little frozen here. Give me just a second, please. We're going to start with section 9.1, which is about estimating a population proportion. So the objectives in this section are to first be able to obtain a point estimate for the population proportion, and then you need to be able to construct and interpret a confidence interval, determine the sample size necessary for estimating a population proportion within a specified margin of error. So let's start with obtaining a point estimate. So a point estimate, and we've done this before, this was in the last chapter as well, but it's just the value of a statistic that estimates the value of a parameter. And really what we do is we define it as p hat equals x over n, where x is the number of individuals in the sample with some specified characteristic, and n is the sample size. So let's take a look at this one. In July of 2008, the Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder, and 1,123 were in favor. So if we want to obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder, all we would do is we'd take the 1,123 who were in favor from our sample and divide it by our sample size, which was 1783. And if you divide that, you actually get 0.63. So that's going to be the point estimate that we're going to use for our registered voters nationwide, and it's based on our sample data. Now what we can do is we can use that and we can construct and interpret a confidence interval for the population proportion. So a confidence interval for an unknown parameter just consists of an interval of numbers that is based on a point estimate. Now, the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. And the level of confidence is denoted as 1 minus alpha times 100%. So, for example, a 95% level of confidence, which would mean that alpha equals 0.05 because you just take 100 from your level of, or take 100 minus your level of confidence and then change it to a decimal. That's going to imply that if 100 different confidence intervals are constructed, each of them based on some different sample from the same population, 95 out of those intervals would contain the parameter and 5 would not include the parameter. So confidence interval estimates for the population proportion are of this form. You take your point estimate, okay, which was your sample proportion, and then you add and subtract the margin of error. The margin of error of a confidence interval just estimates basically, or measures how accurate the point estimate actually is. So margin of error depends on 3 different things. It depends on level of confidence, okay, and as the level of confidence increases, the margin of error is also going to increase. Sample size. As the sample size increases, the margin of error is going to decrease. And then standard deviation. So the more spread that there is in a population, the wider our interval will be for some given level of confidence. So for a simple random sample of size n, the sampling distribution of p hat is approximately normal with mu of p hat equal to p and the standard deviation equal to the square root of p times 1 minus p over n, provided that n times p times 1 minus p is at least 10. And we also require that each trial be independent when we're sampling from finite populations. So n has to be less than 5% of your actual population size. And this should be reviewed. This is from the last chapter as well. So if we want to construct a confidence interval for the population proportion, let's suppose that a simple random sample of size n is taken from a population, and we want to create a 1 minus alpha times 100% confidence interval for p if we're given the following quantities. So our lower bound, what we're going to do is we're going to take our point estimate and we're going to subtract, and this is our critical value, we'll have to look this up on the table, z alpha over 2. And then we multiply that by the square root of p hat times 1 minus p hat over n. And then to get the upper bound, it's exactly the same, but instead of subtracting, we add. And it has to be true that n times p hat times 1 minus p hat is at least 10, and n is less than 5% of your population. Otherwise, we cannot construct this interval. Now, in order to interpret the confidence interval, what you're going to say is a 1 minus alpha times 100%. So you're going to put your level of confidence there, 95%, 90%, 80%, whatever you're talking about, indicates that 1 minus alpha times 100% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. Okay, so margin of error in this case is the value that we add and subtract from our point estimate. So we find our margin of error by taking our critical value, our z alpha over 2, and multiplying by the square root of p hat times 1 minus p hat over n. So let's take a look at this example here. Same university poll, 1,123 were in favor of the death penalty for people who are convicted of murder out of our 1,783. And we'd like to obtain a 90% confidence interval for the proportion of registered voters who are in favor of the death penalty. So a couple things we need to check. First, we need to calculate p hat, which we've already done. That was 0.63. That was taking our 1123 and dividing it by our 1783. And then we need to make sure that n times p hat times 1 minus p hat is at least 10. So we take our 1783, which was our sample size, and we multiply it by the point estimate that we obtained, which was 0.63, and we multiply it by 1 minus 0.63 as well, and we get 415, which is obviously greater than or equal to 10, so that's not an issue. And then the sample size has to definitely be less than 5% of the population, and in this case it certainly is, because we're interested in all registered voters, and our sample is pretty small, it's less than 2,000. So since we want a 90% confidence interval, that means that alpha equals 0.10, because all you have to do to find the alpha level is take 100% and subtract the confidence interval that you're wanting, in this case 90%, and you change it to a decimal, which is 0.1. So in order to find z alpha over 2, you take your 0.10 and you divide it by 2. And so really what we're looking for is z of 0.05. So you have a couple of options. One is to just look for 0.05 in the table, and that's going to be your z, except you use the positive version. But kind of what you want to maybe keep in mind is that we're normally constructing either a 90, a 95, or a 99% confidence interval. And if you look at the pullout table in your textbook, or if you look back at the appendix where they have the normal distribution, there are some critical values there that are used very often. You may want to memorize these so that you know them. It might make your life a little easier rather than having to look up the critical values on your table. But 1.645 is the critical value for a 90% confidence interval. So in order to actually create our confidence interval, all we have to do is take our point estimate, which is our 0.63, and then we add and subtract this z, which is 1.645, and then we multiply that by the square root of 0.63 times 1 minus 0.63, so that's our p hat times 1 minus our p hat, over n, which was 1783. And if we add and subtract it, we get 0.61 to 0.65. And you'll notice that our point estimate of 0.63 is smack dab in the middle of these two numbers, and that should always be the case because you're adding and subtracting the same margin of error. So your point estimate should always be right in the middle. So in order to actually interpret this, we would say that we are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is somewhere between 0.61 and 0.65. Or we could say 61% and 65%. Okay, now the third objective in this section is to be able to determine the sample size that's needed for estimating a population proportion. So in order to do that, all you have to do is take p hat, which is your point estimate, times 1 minus p hat, and then you multiply that by the critical value divided by e, which is a specified margin of error, and you square that. But you just square this last part, not the entire thing. So you might, in your calculator, want to do this portion first, your division, square it, and then multiply by these two numbers. Now, The formula uses p hat, which depends on n, which is the quantity that we're trying to determine. So we have two kind of possible solutions for this. First is to use an estimate of p hat based on some pilot study, okay, or an earlier study. And if you have a pilot study or some earlier study, then that's a great route to go. But if you do not, if this is kind of the first study that's done on this, or you think that the first study that was done is not very reliable, what you can do is you can actually let p hat equal 0.5. And that gives the largest possible value of n for a given level of confidence. So if you think about the value of p hat times 1 minus p hat, the kind of largest value, if you think about what this graph of this would look like, because really this is negative p squared plus p, it's going to look like this. And then the maximum is actually going to be obtained right smack dab in the middle when when p hat equals 0.5 and 1 minus p hat is also 0.5. So 0.25 kind of gives us that maximum value. So we have this formula here, okay, which is one way to estimate it. Or we have this one here, which uses 0.25. You're going to use this one if you have no prior estimates. You're going to use this one right here, where you have p hat times 1 minus p hat, if you want to actually use a prior estimate. Okay, so a sociologist wanted to determine the percentage of residents of America that only speak English at home, and we want to know what size sample should be obtained if she wishes her estimate to be within 3 percentage points with 90% confidence, assuming that she uses the 2000 estimate obtained from the census, or a census survey, which was 82.4%. So let's pick this apart. If you look back, she wants her estimate to be within 3 percentage points, so the margin of error here is 0.03. Z alpha over 2 is going to be Z of 0.05 because we're interested, again, in 90% confidence. So this is going to be 1.645. The prior estimate that we have is 82.4%, so our p hat is 0.824. So we just do our n calculation by taking our p hat, which is our 0.824, multiplying by 1 minus p hat, and then we take 1.645, which is our critical z value, divide it by the margin of error that we're happy with, and then we square just that part of the value, and you should get 436.04. Now, one really important thing to note, so that you get these correct when you do them in your homework and on your quizzes, is that you always round up, okay? So for sample size calculations, we have to round up every single time. Because if we only surveyed 436 people, not 437, we wouldn't quite meet the specifications that we're looking for. We would maybe have a slightly larger margin of error, or yeah, something like that. So we have to, or we wouldn't have 90% confidence. So we have to make sure that we always round up our sample size calculations. So this answer is going to be 437. So the sociologist has to survey 437 randomly selected American residents in order to get a read on this data. Okay, now section 9.2 is about estimating a population mean. So we just did population proportion. Now we're going to take a look at population mean. So the objectives in this section are pretty similar. We want to obtain a point estimate for the population mean. And then we're going to learn about students' t-distribution. We're going to learn how to determine t-values, construct intervals, and find sample sizes. Okay, so it's pretty much the same process with population proportion, except we have a couple of kind of extra steps because we're going to have to use this new distribution, the t-distribution, and we'll talk about why when we get to that. But the first objective is just to be able to obtain a point estimate for a population mean. Now, you should already be familiar with this from Chapter 8, but a point estimate is just the value of a statistic that estimates the value of a parameter. So for example, the sample mean, x bar, is a point estimation for the population mean of mu. So we've used this example a couple of times with pennies, but we have pennies that are minted after 1982. They're made from 97.5% zinc and 2.5% copper. And then the following data actually represents the weights of 17 randomly selected pennies that were minted after 1982. So we have all of these different weights. We want to treat the data as a simple random sample, and we want to estimate the population mean. So you could use StatCrunch for this, or your calculator, or whatever, or this isn't that many observations. You could add them all up by hand and divide by 17. And what you should actually get is 2.464. So your point estimate of mu is just 2.464 grams. Now, objective 2 is to be able to state the properties of a student's t-distribution. So let's go through this and we'll talk through why we use it in just a minute. But let's suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, then the distribution of t equals, and you take x bar minus mu and divide it by s over square root n. It's going to follow a student's t-distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. So let's take a look at this. We're going to compare the standard normal distribution to the t-distribution using simulation. Okay, so this is going to allow you guys to see the difference. So we're going to obtain 1,000 simple random samples of size n equals 5 from a normal population with a mean of 50 and a standard deviation of 10. We want to determine the sample mean and sample standard deviation for each of the samples, compute z and t, and draw histograms. So the important thing here is our histograms. We have our histogram for z and we have our histogram for t. Okay, so if you look at these, let me give you guys just a second to actually take this in. Here's our histogram for z and our histogram for t. So z again and t. The conclusions that we can make are that the histogram for z is symmetric and it's bell-shaped. Okay, it follows a normal distribution, and virtually all of the rectangles are between -3 and 3. So if we take a look, this is probably around -3 and 3. And for t, it's also symmetric and it's also bell-shaped. The center is also at 0. But if you look back at the tails, let me go back to them. These tails are much, much longer. Okay, so we have bars that are all the way out at -10. So t is basically just more dispersed. So it's unlikely that t follows a standard normal distribution. The additional spread in the distribution of t is attributed to the fact that we use s to find t instead of sigma. Because the sample standard deviation is itself a random variable rather than some constant, we have actually more dispersion in the distribution of t. So here's kind of a summary of the properties of the t-distribution. It's different for different degrees of freedom. So if we look at different sample sizes, the t-distribution is going to change. It's centered at 0 and it's symmetric. The area under the curve is 1. The area to the right of 0 is 1/2, and to the left of 0 is also 1/2. And then as t increases or decreases without bound, the graph is going to approach but never equal 0. In addition, the area in the tails of the distribution of t is a little greater than the area in the tails of the standard normal distribution, since we are using s as an estimate of sigma, thereby introducing basically just further variability. But as our sample size increases, the density curve of t is going to get closer and closer to the standard normal density curve. This result occurs because as the sample size n increases, the values of s get closer to the values of sigma by the law of large numbers. So if we take a look here, we have our normal distribution in blue. Okay, so you see it's a little higher here, and then the tails are not very long. We have in red n equals 15, okay, which looks a lot like our normal distribution here. The tails are a little bit higher, but not too much. And when we only had n equals 5, we had it shorter up here, and we had quite a bit longer tails. So you can see the difference between n equals 5 and n equals 15 is basically in the tails here. The one with the smaller sample size has larger tails. Larger sample size looks more like the standard normal curve. Okay, so one thing that we need to be able to do is actually determine t values. So the notation t alpha is just the t value such that the area under the normal curve to the right is alpha. So if you look here, we have t alpha, the area to the right is alpha. So let's say that we want to find a t value such that the area under the t distribution to the right of the t value is 0.2, assuming that we have 10 degrees of freedom. So what we're trying to find is t of 0.2 with 10 degrees of freedom. So what you need to do is either use a table or some kind of statistical tool in order to find this, okay? And what we're looking for is we're looking for t of 0.2, so we're looking for something where the area is 0.2, and you want to make sure that you're looking for 10 degrees of freedom. So the unknown value here is labeled and the area is shaded. And if you actually look for this on your table, you're going to find that the value is going to be 0.879. So that is our t value, where the area to the right is going to be 0.20. So now that we know how to calculate a t-value, we're going to use it to construct and interpret confidence intervals for our population mean. So the reason that we use t-intervals for confidence, or sorry, that we use t-values for confidence intervals for mean is that we do not know our population standard deviation, okay? So we have to actually use student's t, which allows us to use the sample standard deviation instead. So a couple of things have to be true. Our sample data has to come from a simple random sample or a randomized experiment. The sample size has to be relatively small compared to the population, meaning that it can't be more than 5% of our population. The data has to come from a population that's normally distributed, or the sample size has to be large enough. So if we have a 1 minus alpha 100% confidence interval for mu, what we do is we take x bar, which is our sample mean, and then we add and subtract our critical value for t, which is t alpha over 2 with n minus 1 degrees of freedom, and then we multiply that by s over square root of n. So we're going to look at an example here where we've used Minitab to simulate obtaining 30 simple random samples of size n equals 8 from a population normally distributed with a mean of 50 and standard deviation of 10. And we want to construct a 95% confidence interval for each of the samples. And we want to know how many of the samples are going to result in an actual interval that contains mu equals 50. So if we take a look, we have I'm going to just scroll through these real quick. We have 30 confidence intervals on these 2 pages. And what we're looking for is, well, the mean of 50 should be contained within the confidence interval. So for example, if we look at this first confidence interval, our 95% confidence interval is from 40.14 to 54. That does contain 50. Okay, so that one is good. And if we kind of look our way down, these all contain 50. This one that's highlighted does not contain 50 because it goes from 52.7 to 66.5. So that's one of the ones that doesn't. And then if we look on our next page, all of these contain 50. This one also does not. Okay, so our mean was found to be 61.42 for this sample, which gave us a confidence interval from 54.5 to 68.4. So we can kind of note that out of the 30 actual samples that were obtained and the confidence intervals that were created from those samples, 28 of them, which would be 93% of the confidence intervals, actually contain a mean of 50. Now, in general, for a 95% confidence intervals, any sample mean that lies within 1.96 standard errors of the population mean are going to result in a confidence interval that contains mu. So this is pretty close. We got 93% compared to the 95% confidence that we wanted. And probably if we took a few more samples, we would see that we would get 95%. So whether a confidence interval contains mu depends solely on the sample mean x bar. So if you look back here, the reason that these didn't contain, this one in particular didn't contain our sample mean of 50 was because the mean, or our population mean of 50, sorry, is because the sample mean of 61 was so high. And if you look at this one, the sample mean was 59.62, which is also quite high, okay? So let's go ahead and actually construct a confidence interval. So we have this data here where we have pennies, and you probably want to look at a normal probability plot first. This one looks fine. And it's nice to look at a box plot as well. So in order to actually create a lower and an upper bound, what we do is we take our x bar, which you would want to use either your calculator or StatCrunch or some other statistical tool like Excel in order to actually find your x bar. So this is your mean of 2.464. You also need to make sure that you calculate your S, which is going to be your sample standard deviation, which again can be done in any of those tools, and you should get 0.02 for that. So in order to get the lower and the upper bounds, you take 2.464, which is your x bar, and then you add and subtract your critical value, which if you look it up on the table is going to be 2.921. And then you multiply that by S, which is 0.02, divided by square root of 17, because that is your sample size. And you end up with a lower bound of 2.450 and an upper bound of 2.478. So we can say that we are 99% confident that the mean weight of pennies minted after 1982 is somewhere between 2.45 and 2.478 grams. Okay, so objective 5 in this section is to be able to find the sample size that's needed to estimate the population mean within a given margin of error. So this calculation is similar to the one that we saw before. What we actually have to do is we have to take z alpha over 2, multiply by s, divide by the specified margin of error e, and square it. So let's go back to our pennies. Let's figure out how large of a sample would be needed to estimate within 0.005 grams with 99% confidence. And we want to assume that our population standard deviation is 0.02. So in order to do this, we need to look up a critical value. We want 99% confidence. That means that alpha over 2 is 0.005 because alpha would be 0.01 or 1%. And you get 2.575 is that critical value. S is going to be, I don't know why this said sigma, this should be S, which is 0.02. Your margin of error should be 0.005 because we want it to be within 0.005 grams. So in order to get our sample size calculation, we take our critical z value, which was 2.575, we multiply it by our sample standard deviation of 0.02, divide by the margin of error, which is 0.005, and then we square that. And you should get 106.09. Again, we have to round up for the same reasons as last time. We should get 107. So in section 9.3, there's nothing new, but this is just going to put everything together so that we can talk about, again, the assumptions and what types of methods we know. So if we're estimating a parameter of a population proportion, okay, so we're looking at a parameter for a proportion, provided that n times p hat times 1 minus p hat is at least 10, we can construct a confidence interval, and that was what we learned how to do in the first section. Now, if you're trying to estimate the population mean, mu, then it depends on if sigma is known or not. Typically, no, sigma is not known. Now, if n is at least 30, then we compute a t-interval, which is what we just did. If n is not greater than or equal to 30, then if the data comes from a normal population without any outliers, we can still compute a t-interval. But if it doesn't, then we would have to use non-parametric methods, which is outside the scope of this class. Now, if sigma is known, then if n is greater than or equal to 30, we can compute a z-interval. If it's not, then if the data comes from a normal population, we can still compute a z-interval, but if not, then we would have to use non-parametric methods, again, outside of the scope of this class. And standard deviation or variance we're not doing in this course either. But it's important to kind of note that when you're doing proportions, we just calculate a z-interval using kind of the rules that we had. When we have a mean, though, typically we're doing a t-interval because normally we do not know our population standard deviation.